Alright, calm. AQA A-level chemistry topic 4 completely patterned. Yeah, we're gonna go through all the PMT questions, yeah, so you can do practice on that, yeah. And yeah, this is for energetics. Alright, calm. Remember as well, yeah, this channel is my channel as much as it's your channel, yeah. So like let me know any suggestions, anything I can change, I'll change it, innit? Alright, cool. Question 1A, yeah, easy. So state the meaning of the term standard enthalpy change of combustion, yeah. So this is basically the enthalpy change when 1 mole. So it's an enthalpy change when 1 mole of a substance burns completely in oxygen with all substances in their standard state, yeah? So what that means here is basically 1 mole of substance burns completely in oxygen, yeah? You can't just say it burns in oxygen, yeah? You need to say completely, yeah? Because it could be incomplete combustion, yeah? With all substances in their standard state, yeah? Alright, calm. Next one, yeah? Question 2. A student uses whatever propanol, yeah, with that MR, combustion of that many grams of the propanol, temperature increases from that to that. Calculate the enthalpy basically, yeah. So to calculate enthalpy, yeah, you need to find the energy and then divide the energy by the moles, yeah. So let's find the energy first. The energy is very easy, yeah. Use the same formula for all of these, yeah. Q is equal to MC delta T. Now, M is the mass of water, yeah, because that's the thing you're actually increasing the temperature off, right? So it wouldn't make sense to take the mass of propanol, yeah. It's the mass of water, yeah. And then C is always 4.18. And then delta T is just 35.1, yeah, minus 21.2, yeah, which would give you 13.9. And now, very easily, yeah, you can find Q. So what's Q then, yeah? Q would be basically all that put together, yeah, which would give you 87.3 joules, yeah? Calm, minor. Now, what do I need to find? Now I need to find the moles, yeah, because enthalpy is just energy divided by moles, yeah? So now I need to find the moles, yeah? So the moles, yeah, N of propanol, yeah? And then N of that means moles of that, yeah? That's just going to be the mass divided by the MR, yeah? The mass is 0.497, yeah, it tells you. And then divide that by the MR. The MR is going to be 60. So that's going to give you moles, yeah, of 0.008. No. Yeah? Now, now what I need to do is I need to find delta H, yeah? So that's enthalpy, yeah? Enthalpy is going to be, yeah, in kilojoules per mole. So I need to change this joules value into kilojoules, yeah? So that's going to be 8.7153, yeah? Yeah. Divided here by so just divide that by 1,000 and then divided that by the actual moles, yeah. So the moles is 0.00828, yeah. So now what I can do is I can just do that and then I find the enthalpy in kilojoule per mole, yeah. It will be 1050, yeah. But because this is exothermic, yeah, this is combustion, yeah. Therefore it's gonna be negative. So therefore it's negative 1050, yeah. Calm, easy. Next question. The enthalpy of combustion determined experimentally is less exothermic, yeah? So give one possible reason other than heat loss, yeah? So a reason other than heat loss, yeah, would basically be incomplete combustion, yeah? Because if the combustion is incomplete, yeah, then therefore what that means here is it will have certain situations to it, you know what I'm saying? If it's incomplete, yeah, it will be a matter of like it would release less heat, yeah. Complete combustion completely burns it, so it will release more heat. It will be more exothermic, yeah. Whereas if it's incomplete combustion, it's gonna release less heat, yeah. Alright, calm. This question is about enthalpy changes, yeah. Define the term enthalpy change, yeah. So this is easy, yeah. This is just heat energy, constant pressure, yeah. Minor. Next one. Propane undergoes complete combustion, yeah. This is this, whatever. Alright, calm. Now let's see what he's saying, yeah. So what he's saying, let me just look bigger like that, yeah. Calm. Now we're talking. Calm. So what we can say here, yeah, is we need to just do bonds broken minus bonds made, yeah, the left hand side minus the right hand side, yeah, because breaking bonds requires energy, so it's positive energy, yeah, whereas making bonds releases energy, so it's negative, yeah. So It's easy GCSE type question, yeah. Let's look at all the bonds here. I've got two CC bonds here, and I've got eight CH bonds. So effectively, yeah, if we look at our bonds broken, yeah, so just write broken, yeah. So broken is gonna be, yeah, two times two CCs plus eight CHs plus the 5O2. So there's O bonds, so five O bonds, yeah. Come. Now let's look at what that actually gives you, yeah. If you do 8 times 412 and you do 5 times 496 and you add them together, yeah. CC is the unknown bond that you're trying to find here. So what it will do, yeah, is it will give you 5776 here. Calm. Easy, yeah. Calm. Now let's look at this here. So 2CC plus 5776. So that's bonds broken, yeah. Now let's look at bonds made. Bonds made is the right hand side, yeah. So that's basically, yeah, six CO bonds, yeah, because there's two COs, two CO bonds in this, CO and CO, and then times it by three, so six CO bonds, yeah. Plus how many H2O? Well, there's two OH bonds in H2O, yeah, times it by four, eight OH bonds, yeah. Calm. So if there's eight OH bonds here, that's just gonna be 8 times 463, and then plus 6 times 743, yeah. So do that, yeah, and then you're gonna get in total, yeah, you're gonna get 8162. Calm. So now make sure you write this down, yeah, because I'm gonna clear the screen, yeah. So write this down. So we got bonds broken is that, bonds made is that. So now let's write this down. Calm. So now what I can say, yeah, is I need to do bonds broken minus bonds made, yeah, because yeah, so left minus right hand side would give me that total, yeah. So what I can say now is I can say that 5776 here plus 2cc minus 8162 here. And then also deep it from liquid to H2O from to gas H2O is 41 kilojoule per mole, yeah. Now to go, but I'm making liquid here, so I'm going from gas to liquid, so I need to reverse this. So I'm gonna do minus 41. And also, how many H2Os am I making? I'm making four, yeah. So it'd be four times the 41. Does that make sense? Yeah. So like this, yeah. So minus 41, yeah, times 4. Calm. Yeah. And that's going to give me the total enthalpy change here, which is minus 2046, yeah. And now just rearrange for 2cc, yeah. And what you'll find here is that if you do that, so bring 41 times 4 to the other side, bring 8162 to the other side, minus 5776, and then divide by 2, you'll see that cc is equal to 252, yeah. So that's the enthalpy change. Calm. Easy. Oh, yeah, by the way, yeah, this is negative, yeah. Yeah, yeah, calm. I wrote negative. Cool. Explain why the value given for the OO enthalpy in part B is not a mean value, yeah? Well, bruv, mean value, yeah, means that you take like bare different values and then you divide it by the total number of values that you took, right? So OO bond, yeah, is only found in oxygen, bro. In O2, that's the only place where you find the OO bond, yeah? So oxygen, so therefore there's no mean because there's not, mean is you take a variety of different substances, yeah? And then you divide it by the total number. But here you can't do that because it's just OO is just oxygen according to the mark scheme, innit? Yeah. Alright, calm. Question three, yeah. The student does an experiment to determine the value for enthalpy of combustion of heptane, yeah. Figure below, design a table to record all the readings necessary to determine an experimental value for the whatever, yeah. Alright, calm. Let's do that then, yeah. So table, yeah, liquid table thing, fam. So just basically we're gonna need to record temperature, initial, final, delta T, yeah, because it's like some enthalpy changing questions, yeah. And then also I'm gonna find like how much mass was burned, right? So I need to calculate the burner weight before and then the burner weight after, and that will tell me, yeah. So I can just write here temperature in Celsius, yeah, and then what we can do is I can write here initial, yeah, final, yeah, and then delta T, or change in temperature, yeah. And then I can write here, mass in grams, yeah. And then what I can write here is I can write same thing like I write there. I can write burner before, so burner mass before, yeah, burner after, and then change in mass here, or mass burned, yeah. So that's the full table. So it will look like that. Yeah. Cool. And I can't move this on the why it's not allowing me, fam. This should be a little bit before, yeah, like that. So I can do that. Yeah. That's the table, yeah. The student considered using a glass beaker on a tripod and a tripod, yeah, gauze instead of the clamped copper calorimeter, yeah. So just two disadvantages of using a glass beaker on a tripod and gauze, yeah. So effectively, yeah. The glass is a poorer conductor than copper, yeah. And also tripod and gauze, yeah, would reduce heat transfer as well. Yeah. So so one point in this is to, transfer it, you know what I'm saying? Transfer the heat, right? So you see how this, I'm measuring the water. I want the burner to actually burn and transfer into the water. So if I didn't use copper, bruv, if I use glass, it's gonna be a lot, like it's gonna stop energy transfer. And also if I put gauze and shit, it's gonna do the same shit. It's gonna reduce energy transfer, yeah? Yeah. So just two reasons here why the value of the enthalpy of combustion from the experiment is less than endothermic from the Delta book, yeah? So obviously this is just, bro, this is standard, and just say like heat loss, yeah? These are easy marks here. And then just say some other bullshit. Just say incomplete combustion. Alright, minor. Next one. So just one addition to this apparatus here that would improve the accuracy, yeah? So one addition to the apparatus there that could improve the accuracy, yeah, of the experiment, yeah? So what you can say, yeah, is you wanna reduce the heat loss basically, yeah. So what you can just say is you can just say use a lid, yeah. Here they got use a windshield as well, but you can say allow, it says allow use a lid, yeah. So you can just use a lid, yeah. Cool. There's questions about enthalpy changes, yeah. State the meaning of the term enthalpy change, yeah. Easy, easy, man. No problem, mate. I'll state it for you 10 times, bro. Yeah, heat energy change at a constant pressure, yeah. Man, no, bro, yeah. They think they can get to man, yeah. They can't, fam. Student determines whatever, calm. Student measures out 50 centimeter cube of 1 mole per dm cubed aqueous using a measure whatever, weigh out 2.5 of sodium calcium carbonate, calm. The student uses data to determine the value, yeah. Explain how experimental method of the apparatus can be improved, yeah. Calm. So this one, yeah, read it out, yeah. Normally I skim through questions in it, but because normally like the waffle is not even needed. But this one it kind of is in it. So read it, yeah. Essentially what he's saying is just like provide a better method for my man of how you can pattern the experiment differently, yeah. So this one here is a bit long. You can say bear over here, yeah? So first thing I would say, yeah, is use a biret, a barrette, yeah, or pipette instead of a measuring cylinder, yeah, for more precise measurement of the volume of 1 mole per dm cubed, yeah, HCl. Calm. Yeah, also, yeah, use a polystyrene cup or insulate the beaker, yeah, to minimize heat loss, yeah, to surroundings. Calm. And then also what you can do, yeah, and maintain a more constant temperature during the reaction, yeah. You see that, fam, yeah? They hit us with these bare 6 markers, whatever, yeah, long 6 markers, yeah. But bro, we got it patterned, man. Don't worry. After adding the solid calcium carbonate, yeah, reweigh the watch glass, yeah. That's a common one. After adding the solid calcium carbonate, yeah, reweigh the watch glass here to determine the true mass of reactant used. Calm, and then you can use powdered calcium carbonate, yeah, instead of the chunks here. My man, yeah. Instead of the chunks here, to ensure a more uniform and rapid reaction. Because deeper, yeah, there's going to be a more surface area if it's powdered, yeah, so it's going to be quicker compared to if it's in chunks, yeah, because you're increasing the surface areas that it can react. I then record the initial temperature of the solution, yeah, before adding the reactant. And then record, yeah, record the temperature at regular intervals until a consistent trend is observed, yeah, when you add the reactant, yeah. And then plot a graph against time. This is guaranteed 6 marks, man, yeah. And then obviously extrapolate, yeah. Extrapolate the graph. If you don't know about this here, go watch the content video, yeah. Graph to the point of addition of the reactant, yeah. So the point where you added the reactant where the reaction started, yeah. And then determine the temperature change, yeah. Calm, minor, easy, man, honestly, yeah. Alright, calm. Let's look here. Next question, yeah. In a different experiment, 50 centimeter cube of whatever was used, the initial temperature, this. Look at the question they're actually trying to ask here fully, yeah, and then look at what they want later. So calculate the maximum final temperature of the reaction, yeah. So to do that, yeah, I'm gonna need to use like a Q equals MC delta T situation in it, yeah. What else do I need to do? Um, that's it. So basically, yeah, what you're gonna need to do is you need to find Q, calm. So how I can find Q, yeah, is it gives me the delta H, right? Yeah. So it gives me delta H, yeah, and I know that Q is equal to what? Q is equal to, because I'm gonna need to use Q equals MC delta theta to find delta theta, yeah, or delta T, yeah, and Q, yeah, is gonna be equal to delta H, yeah, times the moles, because deep it. Enthalpy is equal to energy divided by moles, yeah. So if I rearrange that, yeah, if you man wanna don't get that, yeah, then here. So times that up here, and then you get Q. Alright, calm. So what you want to do here is we want to find Q in it. So therefore, what I'll say here is Q is equal to 57.1, yeah, times the moles. We don't know the moles though, yeah, so let's find the moles in it. So the moles, yeah, of whatever it is, yeah, is going to be equal to the concentration times the volume. The concentration of both is 0.500, yeah, of reactant, yeah. So 0.500, yeah, times that by the actual that's the concentration, yeah, times that by the volume, yeah. But the volume needs to be in dm cubed. So I need to divide the 50 by 1000, yeah, because that's cm cubed. It will get translated into dm cubed, yeah. So then the moles that I've got is 0.025 moles, yeah. So now easy, times 57.1, yeah, by 0.025, yeah. Calm. And then that's gonna give me, yeah, 1.4275 kilojoule, yeah. Minor. Now I've got that information, yeah. Now I can do the actual Q equals MC delta theta, yeah. So Q equals MC delta T, yeah. And then I'm gonna say delta T therefore would be equal to Q over MC, yeah. So Q is what? Like MC, you know what I'm saying? Alright, cool. Q is what, yeah? So it's 1.4275, yeah, times 1000, because I'm gonna need to change that into joules, yeah. So times it by the kilo, yeah. Like a brick, yeah. Alright, cool. And then yeah, divide it by the MC in it. So the M is obviously the M, bro, is the total. Basically, yeah, when you got a liquid, yeah, and you're doing these kind of enthalpy questions, yeah, the volume of the liquid in cm cubed, yeah, is the mass because the density is 1 gram per cm cubed. If I've got 50 cm cubed, then it would be 50 grams, right? So the density is the mass. So here I've got 50 and 50, so it's 100 grams in total because it would be 100 cm cubed in total. So the mass is 100, yeah, and then C is 4.18. It's always that, yeah. And then just calculate that, yeah, and you get 3.42, bro, yeah? Pattern, yeah? Get 3.42, yeah? Again, doesn't matter whether it's Kelvin or whether it's degrees, yeah, because it's temperature change, yeah? So now you just add that to the thing that it was before, 18.15. So the initial was 18.15, so 18.15 plus 3.42. 18.5 plus 3.42, yeah, that gives you the final. So TF, which would be 21.92 apparently. So that's the final temperature, 21.92. Easy pattern, man. Calm. Next one. So just how without changing the apparatus, the part in C could be improved by reducing the percentage uncertainty. Yeah. So percentage uncertainty. Yeah. Listen to this. Yeah. Percentage uncertainty. Yeah, is the absolute uncertainty divided by the shit you measured. Yeah, times 100. So if I'm gonna decrease the percentage uncertainty. Yeah. So absolute over shit you measured times 100, yeah? Then what do I need to do? I need to increase the shit you measured, yeah? To basically decrease the overall thing. Because if I increase that, yeah, it's going to be dividing by a higher number, so it'll be a lower number in the output, yeah? So essentially what I need to do here, yeah, is just increase the concentration, yeah? So I increase the concentration of solutions, yeah, then therefore I'm going to have a higher temperature and whatnot, yeah, raise, and then higher temperature, which would therefore mean that the uncertainty would decrease, yeah, because the thing you measured would be increased, yeah. Which reaction has the enthalpy change for equal to the standard enthalpy of formation, yeah? So standard enthalpy of formation is basically when you form something from this constituent standard states, yeah? So A is all gaseous, that doesn't make sense, yeah? Lithium is not gaseous in its standard state, it's a solid, yeah? This is, bruv, you got ions and whatever, yeah? Anyway, this one is also aqueous now, bruv, yeah? This one's the correct one, yeah? So it's from solid lithium plus gas fluorine, yeah? To make solid LiF, yeah? Calm. This one, yeah, this one fucks with people a little bit. But it's easy. So, yeah, let's look at these questions, yeah? So, Fe plus half O2, whatever, yeah? Now, deep this, yeah? I'm trying to make 2 FeO to go to that, yeah? So, what I need to do, yeah, is I actually need to, I actually need to times the top reaction by 2. Yeah. So, yeah, so what I need to do here, yeah? is you need to basically deep, yeah, how is it gonna basically form what you want it to form, yeah? And to do that, yeah, I essentially just need to, yeah, so times the top reaction by 2, yeah, so it'll be 2Fe, yeah. Sorry. So reverse the top reaction, yeah? So reverse the top reaction, yeah, and then times it by 2, yeah? So if I reverse the top, I was tweaking a little bit there, yeah? Reverse top reaction times it by 2, so I'll get 2FeO, yeah? And I'll show you why in a minute. So 2FeO, yeah? Would give me 2Fe, because Fe times 2, yeah? So I'm just timesing the top equation by 2 and reversing it, yeah? And then half O2 times 2 would just be O2. Calm. Now that I've got that, yeah? Now that I've got the 2Fe and the O2, yeah? Now I'm going to use that to then produce the Fe2O3. Does that make sense? Yeah, because you see down here I needed 2Fe to do this reaction, yeah? So now I've got 2Fe. So everything's patterned now, yeah? So now what I need to do, yeah, is just mix it with the bottom reaction, easy, yeah? So now I've just got 2Fe plus 3O2, yeah? 3O2O2 gives Fe2O3. And if you deep this, yeah, I'm gonna write the moles that the shit that's changing in a minute, yeah. But basically this would be the enthalpy for this, yeah, would be what? It would be minus 272 times 2, but because I reversed it, yeah, it would be plus 272. So 272 times 2 would be 544, yeah. And then on top of that, yeah, this is just standard, yeah. I'm going from that reaction to that reaction. Same thing here, yeah. So it would just be delta H would just be minus 822, yeah. Calm. So 544 minus 822, that's going to be the overall enthalpy change, yeah? But just look at what happens here as well on top of that, yeah? Deep it. I want this to be the final reaction, yeah? Now watch this. 2Fe cancels with 2Fe because this is on the left-hand side of the arrow. It's on the right-hand side of the arrow. So when I combine it, these two will cancel, yeah? Now, let's write everything on the left and everything on the right. So 2Fe, yeah? 0, yeah? Plus 3 over 2 O2 is on the left and O2 is on the right. So I need to do 3 over 2 minus 1. 3 over 2 O2s minus 1 O2. Does that make sense? So overall, yeah, it's going to be half O2 to the right. If you do 3 over 2 minus half, yeah? It's going to be half O2 to the left, I mean, yeah? And then that's going to produce what? What do I have remaining on the right hand side? Just Fe2O. Fe2O3, yeah? And that's it. That's the reaction I get. So do you see why I had to reverse the first equation times it by 2? It's because that's how you do it. It will combine and it will cancel. The way that you can straight away clock here is you can straight away clock, calm, I need to make 2Fe. How am I going to make 2Fe using the first equation? Well, flip it and times it by 2. Yeah? Easy. And so the enthalpy change, bro, will just be 544, yeah, minus 822, which would give you minus 278. So it's this one. Yeah? So just 544 minus 822, yeah. Alright, calm. Similar thing going on here, yeah? So clear that. Similar thing going on here, so what going? So yeah, calm. So basically, yeah, what I'm gonna do here, yeah, is I wanna find this as whatever, yeah. So what I need to do again, same situation, yeah. I'm gonna keep the first equation, yeah. Actually no, I'm gonna reverse equation one because I need to produce this. You see this H2 that I need to make, yeah, to go to 2H. So I'm gonna reverse equation one. So reverse equation one, yeah, and you get CH4, yeah, produces C plus 2H2. Calm. Yeah, and delta H for that is going to be 75, yeah? Because I reversed the minus 75 to the other way, yeah? Calm. Now I need to go from H2 to 2H, but how many H2s do I have? I've got 2H2, so I need to times this bottom equation by 2. So I'll get 2H2 goes to 4H. Easy, fam, yeah? And then the delta H for that, yeah, would be 2 times what it was before. So it was 436 before, so it'll be 2 times 436, yeah? Come, and then that makes sense. Look again, it cancels here. Let me just write the full thing, the enthalpy change first, so you man can be satisfied here. But essentially, this will be 75 here from there, plus this reaction enthalpy change, which would be 872 because 2 times 4 3 6 here. And that's gonna give me 947, yeah, so it'll be that. But if we actually look at this as well from a different perspective here, what's actually going on here, yeah? We can also look at how it cancels again. So CH4, yeah, 2H2 and 2H2 are gonna cancel. So now everything on the left hand side, right on the left hand side. So CH4, yeah, that's the only thing on the left hand side. And here the left hand side cancelled. Gives me, yeah, look what's on the right hand side, C. Look what's on the right hand side here, 4H. So again, do you see how that gives me the overall equation, bro? Yeah? After it all cancels out. So do you see how it's perfectly aligns, yeah? Alright, calm. I should probably do the question underneath, innit? It makes more sense. So like here. Alright, calm. So temperature change from 21.8 to 19.2 using calorimetry. The uncertainty of each reading of thermometer 0.1, yeah. What's the percentage change here? Easy. Percentage change, yeah. Again, percentage uncertainty is absolute uncertainty divided by that thing you measured there times 100, yeah. So this is a different situation because this is a measurement. So if it's a reading, yeah, you take the uncertainty as it is, yeah. So the absolute uncertainty is equal to just the uncertainty of the reading, yeah. But if it's a measurement, yeah, you're taking uncertainty twice. So therefore you have to divide the uncertainty by 2. So in this situation, absolute uncertainty is 0.1. But I took 2 readings deep it. When you took this 19.2, you took a reading. Then you took the 21.8, you took another reading. So what I need to do is I need to times this uncertainty by 2. It's 0.1, yeah, plus 0.1 equals 0.2. So the absolute uncertainty is actually 0.2 here, yeah? And then yeah, and then the delta t, bro, is just that minus that. Yeah, that should be pretty easy to do. 21.8 minus 19.2, that gives you 2.6. Yeah. And so if that gives you 2.6 here, you need to just find the total thing. So that's just 0.2 divided by 2.6 here. Absolute uncertainty divided by total thing you measured here, times 100, yeah, which would give you 7.7. Yeah, so that one. Yeah, easy. Come on, man. Yeah. Just, yeah, come on, patterned, yeah. So that's why you do that, yeah. Alright, cool. So okay, this question, yeah, B is mass of fuel burned, and W is mass of whatever, that's mass of whatever, yeah. I wanna create a formula from this, yeah. So what is the formula for? Which expression gives enthalpy of combustion? Yes, enthalpy is what? It's energy divided by thing, yeah. It's energy divided by moles, yeah. So Q over N. So what's Q equal to? Well, first of all, what's N equal to, yeah? N would be the mass divided by the mR. Mass here is, they call it B. So B over mR, yeah? What's Q? Q is gonna be, yeah, MC delta T, yeah, but here they call M W. So W, mass of water, remember, is M, yeah? So WC, and do they call it delta T? Yeah, they do. Delta T, yeah? So now what I need to do is I need to just divide Q by the moles, yeah? So Q over B over MR, yeah? So if I do that, yeah, I'll write it like this because this is the way they write it, yeah? So if I do that, I'm gonna need to divide this by the B over MR, yeah? Remember, when you divide a fraction, something by a fraction, yeah? You keep flip and then you change, yeah? So this has to flip here, and then you times this, you change the sign to times, yeah? So you times it by MR over B, yeah? So what's gonna happen now is that's it, it's pattern, bro. You get C W delta T MR over B, yeah? So that's when you divide a fraction number, you flip it and then you times it, yeah? Alright, calm. And then this is combustion, so it's negative, yeah? It's exothermic, yeah? So which one is that? That's the first one, right? W delta T MR, yeah, calm. Alright, next question. Alright, cool. A lot of waffle, man. A lot of waffle. What's the question? Calculate the heat capacity, yeah? Calm. So I'm gonna need to do some QM delta T situations, yeah? So always when you're unsure what to do in chemistry, yeah, just find the moles. That's the most simple thing to do. Uh I'm assuming because I don't know delta T, yeah, and I've got this little equation. I mean, because I do know delta T and I got this little equation here, yeah. I'm assuming that I need to find Q, and then from Q I have delta T and I'll be able to find C, yeah? So how can I find Q? Well, Q is equal to the Q will be equal to the the energy, yeah, the enthalpy, yeah, times the moles, yeah. So what I can say here, yeah, is I need to find the moles of hexane, yeah. So moles of hexane, yeah, is going to be equal to 2/86. 2 is the grams of hexane over the MR, yeah. So you need to do mass over MR, yeah. So 2/86, yeah. Calm. That's going to give me 0.0233 moles, yeah. Calm. And now what I need to do, yeah, is I need to find now I need to find the actual what Q was, right? So Q, yeah, is going to be the enthalpy, yeah, which is, I know it's going to be, which is 4154 kilojoule, yeah, that's what they mean, yeah, because this is the enthalpy from the combustion, yes, this is not the energy they're talking about here, yeah. And then I need to find, and then, yeah, that's it, basically, yeah, it's easy. So write this down, because I'm going to eliminate it now. And then, yeah, so Q would therefore be, yeah, enthalpy times the mole. So that's going to be, the enthalpy here is, 4154. And times that by the moles here, which is 0.0233. And that gives you 96.65 kilojoule. Yeah? Calm. Now what I need to do, yeah? Again, where this formula comes from here is that delta H is equal to Q over N, yeah? Energy divided by the moles, yeah? So just times N up, you get Q, yeah? Alright, calm. So now I got this here. Now what do I need to do? Well, now, yeah, I've got delta T is 12.4, yeah? So this is very easy now, yeah? I need to do Q equals MC delta. Not even that, because look what it tells me. I can use this formula. Because I can use this formula. Where is it? Yeah, Q equals C delta T. So C delta T here, yeah. So therefore delta T C would equal Q over delta T, which is just 96.65, yeah, over 12.4, which would give me 7.8 kilojoule per Kelvin, yeah. Because this would be in Kelvin, that's in kilojoule, yeah. And that's why I didn't change it to joules, yeah, because it requires it in kilojoule. All right, calm, easy. When the experiment is repeated, yeah, with whatever, find the whatever this is this same rubbish in it. Yeah. So when it was repeated, yeah, find the heat change, yeah. So to do that, yeah, I need Q, yeah, because I'm gonna need to do Q divided by heat change. They mean enthalpy, by the way, yeah. So I'm gonna need to find heat energy, yeah, which is Q, yeah, divided by the moles, yeah. So how can I find Q? I can find Q, yeah, by doing the energy, yeah, times calculate when experiment is heated with 2 moles, the temperature changes recorded 12.12, yeah. Oh yeah, yeah, yeah. This part, yeah. So 7.8, yeah, calm. I was tweaking. That's why you should always read the question, yeah. It says use 7.8, yeah. It says use C cal from the previous question, yeah. So Q is equal to C cal delta T, yeah. Is equal to C delta T, yeah. And I know Q from last question was 7.8, right? Yeah, 7.8. Not Q, I mean delta T, yeah. So therefore, yeah, what I can say here is that um yeah, I can say 7.8, yeah, times delta T, which is 12.12. It has it in the question. Yeah, I was thinking, what's this value? It says if you're unable to find the value for C, use that. Yeah. Alright, calm. So that times that, yeah, is equal to the moles, yeah? Not moles, what the fuck am I talking about? Q, it'll be Q, yeah? Heat energy change will be 95 kilojoules, yeah? Calm. Now that I got that, I need to find moles and just divide them, yeah? So moles of octane, yeah? Is mass over the MR, yeah? So 1142 over 114. And that's gonna be 0.0175 mole, yeah? Calm. Then what I need to do now, yeah, is I need to basically find the enthalpy change here, which is just the Q divided by that. So that's all you need to do here, yeah? So Q divided by moles. So just take the 95, which was Q, and then divide that by the moles, which is 0.0175, yeah? That should give you the answer of 54,000 yeah, 54,000 28, yeah. I think you need to use you can use the actual value here. So this was not 7.8, it was 7.79, yeah. So that's why there might be a little discrepancy when you calculate, yeah, but it's nothing, it's minor. Yeah. So that's the final answer. All right, cool. State why heat change calculated from the bomb calorimeter is not enthalpy change, yeah, because pressure is not constant in the bomb calorimeter, yeah. So, it's not constant, yeah, in a bomb calorimeter. So pressure is not constant, yeah, and enthalpy changes when it's measured at constant pressure, yeah. The only reason, but in a bomb calorimeter, yeah, the volume is constant, yeah. It's sealed. So that's why you find the temperature change. Alright, calm. The thermometer used to measure the temperature change of 12.2 in part B has an uncertainty of that in each reading. Calculate the percentage uncertainty, the use of the thermometer, yeah? Calm. So again, I just told you when you're doing a measurement, you times the uncertainty by 2. So it will be 0.2 instead because you're taking 2 readings on the thermometer, yeah? Even if it goes from 0 to 5, yeah, let's say, yeah? You have to take the reading for 0 and you have to take the reading for 5. Does that make sense? Yeah? On like a ruler, let's say, yeah, you still have to take 2 readings on a ruler. So whenever you like measure something, yeah, then you have to take 2 readings always, yeah. Alright, 0.2, yeah, and then divide that by the temperature change, which is 12.2, then times 100, yeah. That's gonna give you 1.64. It's getting bare laggy now. Calm. Yeah, and then the change here is obviously just use a bigger mass. That delta T is larger, yeah. Because I told you you need to increase this shit on the bottom, yeah. And that would decrease the uncertainty. Calm. Next thing, yeah. So we've got cyclohexane, we've got some long situations. Column. This is actually easy question, yeah. This is asking me to do like easy enthalpy type question, yeah. Find delta T, I think, right? So the student uses that, use the data to find the final temperature, yeah. So let's just find easy the moles of cyclohexane first, yeah. So moles of cyclohexane, yeah. This is gonna be a long video, by the way. Calm. So I'm gonna take the final, yeah, temperature minus the initial not temperature, mass, yeah, grams, yeah. Find the actual mass of cyclohexane because remember, moles is mass of mR, yeah. So 192.730, yeah, minus 192.100 divided, yeah, by the actual mR, yeah, which is 84, and that's gonna pattern me with 0.0075 moles of that, yeah. Alright, calm. Now I need to find Q. Q, yeah, it gives man the enthalpy change, yeah, which is that. So Q is just gonna be the enthalpy change, yeah, delta H, yeah, times the moles, yeah. So it will be, therefore, it will be 1216 here times 0. Oh shit. But I need to turn this into joules, innit? Because, yeah, because Q needs to be joules for that Q because MC delta T experiment, yeah. Unless like was, you know what I'm saying, in a standard, unless it really wants us to calculate kilojoules or whatever, yeah. So that's gonna be 0, 0, 0 add to it, yeah. So times it by 1,000, yeah. And then times it by the moles. So 0.0075, yeah. And that's gonna give man 9120, yeah, joules of Q, yeah. Easy, easy, man. And now what I need to do, yeah, is just find delta T, yeah. So Q equals MC delta T, yeah. And then delta T is gonna equal to Q over MC, yeah. And then therefore I'm gonna do 9120 over the mass of water, yeah, which is 50 grams of water, yeah. So 50, yeah, times delta T, yeah, which is not delta T, for C, yeah, which is 4.18. So do that, and then you're gonna get 43.16.6, yeah. Alright, calm. And that's delta T, so 43.6, yeah. So now what you need to do, yeah, is one delta T, yeah. What you need to do now is you need to actually find the final temperature, right? So the initial was 19.1, yeah. And then you need to add the change in temperature, 43.6 to that. So then you get the final temperature, yeah, which is 62.7, yeah, which is basically 63. Calm. And that's the final answer. Yeah? So that's easy. Pattern, man. Yeah? Initial temperature is here, by the way, 19.1, yeah? Alright, calm. The data book value is whatever, given reason why the practical value was different, yeah? This should be pattern by now, it's just incomplete combustion, yeah? So it's smaller than it should have been, yeah? Alright, see, table 2 gives standard enthalpies of combustion. Use the data to calculate the enthalpy change for this reaction, yeah? So C, I'm breaking 6 C's, yeah? So I'm burning the 6 C's, yeah? Well, actually, I'm creating it, yeah, but essentially that's what I'm doing, right? So it should just, this is very, very easy, man, yeah? Break that, yeah? So 6 times minus 3, not even but forming it, yeah? So 6 times that carbon, yeah? It's just 9, 4, yeah? Plus 6 times minus 286, yeah? And then I'm going to the right, I'm forming the C6H12 here. So if I'm forming it, this is the combustion of that. So I need to flip the sign. So I need to go opposite here. So that'll be 3920. And that's just going to create minus 160. Yeah, so that's the final answer. Alright, calm. Question 12, yeah? When ethanoic acid reacts with sodium hydroxide, yeah, and whatever, assume both solutions have the same initial temperature, have a density of that, calculate the temperature rise, yeah? Calm. So I'll calculate the temperature rise here. I'm gonna need to find basically delta T again, yeah? So it's same processes, bro, yeah? Find the moles. Yeah, it's all the same thing. Find you got delta H here, yeah? You're just gonna do delta H times the moles, find Q, and then you're gonna do Q divided by MC, find delta T, yeah? So by now, if you haven't got the like clocked it yet, yeah? Do it by yourself, innit? Do this one on your ones here and see if you get it correct, yeah? How much space do I got here? Barely any. So move that here. Alright, calm. So let's find the moles then, yeah? First, yeah? Always in chemistry, find the moles, yeah? Yeah? So let's find the moles. N is going to be equal to concentration times volume. Yeah, concentration is 2. Volume reactance is 25 over 1000 because it needs to be in dm cubed. And that's going to give man 0.05, yeah, moles. Easy. Then I need to find Q. So Q is going to be delta H times delta H is 56.1, yeah, times the moles here, which is 0.05. And that's going to give me 2805. Also, actually, fucked up there a little bit. Yeah, again, this is Q, yeah, so you need to times that by 1000, yeah. So I changed it from kilojoules, yeah, into joules, yeah. So times it by 1,000, innit? And then times a mole. And that's gonna give me 2805, yeah? Calm. And then Q is equal to MC delta T, yeah? And therefore delta T is gonna be equal to Q over MC. So therefore that's gonna be 2805 divided by MC, yeah, which is gonna be the mass again is 25 plus 25, yeah. I told you cm cube is same as grams, yeah. So 25 plus 25 is 50, and then yeah, and then times that by delta T, yeah, which was I mean C, which is 4.18, yeah. Calm, and that gives you delta T, yeah, which is 13.4. That's it. That's temperature rise. Easy, man, yeah. Easy, 4 marks, man. Pattern. B. Student recorded that with a polystyrene cup, whatever. At the 4th minute, the student added sodium hydrocarbonate. Draw a best line fit showing the temperature before mixing, yeah? So, essentially, at the 4th minute, yeah? So we just need to do that. And then extrapolate, yeah? To the 4th minute, yeah? So it'll be somewhere there, yeah? I believe it should actually be a little bit lower than that, yeah? Because you see the trend here. So it should be around here. Should be around there, yeah? I'm taking that as 11.2, and then this is about 17.2, yeah? So 17.2, yeah, minus 11.2. This is just a, like, outlier, yeah? So forget about that. You need to take the general trend, yeah? And then that's going to give me 6. Calm. Because that's 17.2 there, and then that's 11.2 extrapolated, so take 6 here. Calm. That's if it's an obvious downfall, yeah? Sometimes it'll be straight, which we'll see in a minute. Alright, calm. This question about write an equation including that for formation of iron oxide, yeah? So this is from the standard state. And standard conditions, yeah? So therefore it's going to be 2Fe. Obviously just write Fe solid, yeah, plus oxygen gas here, and then you can balance it, yeah? But I'm assuming you might know how to balance in it pattern. So just balance it on your ones. But essentially, all it is here is just iron from a standard state, which is solid, plus oxygen, which is normally a gas, gives you Fe2O3. That's it, and then you just balance it, yeah? Alright, calm. This situation, so this is going to use Hess's law, yeah? So, quotation, use this data and equation for that with monoxide to create whatever, yeah? Calm. So, let's do a little like Hess triangle thing here. So, what I can say, yeah, is that from their standard, yeah, so you have the standard raw elements here, like that, yeah? We're gonna need to create from that, yeah? CO, CO2 and Fe, right? Because that's what's gonna combine to create Fe2O3 and 3CO or whatever, yeah? Because it tells us that this equation here, Fe2O3 plus that is 9 minus 19, yeah? So therefore let's create that from raw elements here. And so it's asking to create find the formation, yeah, of carbon dioxide. So to form carbon dioxide, yeah, we're going from here to there basically, yeah? Okay, so we're going from here, C and O, to find O2, yeah? So we need to find this. And then, yeah, we can also form from these like standard states here, Fe2O3 plus 3CO. And then that's gonna go to there, yeah? Alright, calm. So once you got this little Hess thing going on, yeah? What I can say now is I can say this reaction is minus 19, it tells us, yeah? So that's minus 19, so I can write minus 19 here, yeah? Calm. Now, to go from there to there, yeah? I'm gonna need to form Fe2O3. That's minus 822. And I'm gonna need to form 3COs, yeah? So that's 3 times minus 111, yeah? So it's gonna be minus 822, yeah, plus minus 111 times 3. Yeah. And that's in total going to give you minus 1155, yeah? So that's how much to produce that, yeah? Calm. Then, yeah, deep it. To go from this to there, so there to there is the same as going from there and then across, yeah? So if there to there is minus 115, and then there to there is minus 19. So it's going to be minus 115, minus 115, yeah? Minus 19. That's going to be the same as this. Yeah? So that's going to give me a total minus 1174, yeah? Calm. And then how many COs do I have? I've got I've got 3 COs, yeah. So that's how much energy it requires to make 3 COs. I need for each one, right? Because I'm trying to find the standard enthalpy of combustion formation of just carbon dioxide, yeah. So I just need to divide this value minus 1174, yeah, divided by 3, yeah, to find how much for one, yeah. That's gonna give me minus 391.3, yeah, which is basically minus 391. It's lagging a bit. Calm. So does that make sense here? It's very easy, yeah? So you just create this Hess triangle situation here, and then it becomes pretty simple. Calm. Next one. C, yeah? Some enthalpy values are given, that. Use the data from data 2 to create that, yeah? Alright, cool. So essentially, yeah, I'm going from N2 to NH to N, to just normal N, yeah? To N, yeah? So I'm gonna need to do 944. And then on top of that, yeah, I'm going from H2 to that, right? But I'm doing 3 of those. I'm going from 3H2 to basically 6H here, yeah? So I'm going to need to do 3 times that, yeah? And then, the bond enthalpy for NH is how much the NH bonds are made, right? So how many NH bonds do I have here? I've got 3 in NH3, right? N connected to 3H's, yeah? And then I'm going to times that by 2, so I've got 6 NH's here, yeah? So you just do bonds broken, yeah, minus bonds made, yeah. So the left minus the right, yeah. So it's very easy, and that's gonna give me the overall minus 92, which is the whole energy, yeah. So that's all I need to do here, bro, yeah. 944, yeah, plus 3 times 436, yeah, minus 6. I can call this bond NH, I can call it just Y, yeah, is equal to minus 29, minus 92, sorry, yeah. And then that means that Y is gonna be, if you just rearrange that, yeah, so bring 944 to the other side, bring 3 times that to the other side, then divide by minus 6, yeah? Y is going to be 391, yeah? So that's the final answer. Calm. Give one reason why bond enthalpy. In calculating C is different from the data book, yeah? So this is, I told you about this, even I warned you about it in the content, yeah? This is minor, yeah? So data book here is an averaged value derived from different compounds. So therefore, the actual experimental value is going to be different because that's not an average value. That's just that experimental one that you took here. All right, calm. A student planned to carry out an experiment to determine the enthalpy of reaction of magnesium displaces zinc. All of this here. Show by calculation which reactant was in excess, and then use the data to calculate the experimental value. Yeah. So find which one is in excess. Let's do that first. Yeah. So that means I need to find basically whether ZnSO4 or magnesium was in excess. Yeah. So basically, let's just find the moles of both of them, yeah? And the one with the higher moles will be in excess. So let's find the moles, yeah? Got space here, yeah? So, making from zinc sulfate, yeah? Alright, calm. So ZnSO4 is equal to the moles, yeah? So to find moles, yeah, I'm going to need to do concentration times volume, yeah? So concentration times volume, what's the concentration? 1. and the volume is 50, but divided by 1000, yeah? Because I need to change it into dm cubed, innit? So therefore, yeah, man's gonna get this. Yeah, calm. Then, yeah, I need to find moles of magnesium, yeah? Which is basically gonna be 2.08 over 24.3. Because I've got the mass of magnesium, which is 2.08, yeah? And I know the MR is 24.3, yeah? Which you can get from periodic table, or it might even say it here. 0.3, yeah? Don't make man's mistake out here like that, yeah? 0.3, yeah? That's calm. Yeah? And then that's gonna give you how many moles, yeah? That's gonna give you 0.0856 mole. So hence here, what I can say is that magnesium is an excess here because 0.0856, whereas that's 0.05 here. So the reactant excess here is magnesium. Calm. Yeah? What's going on, man? There? It's tweaking. Alright, cool. And enthalpy of reaction, yeah. So Kj mole there, yeah. Alright, calm. So what I can say now, yeah, is I need to just find I need to just use Q equals MC delta T in it because I'm trying to find enthalpy, right? So I need to find Q and then I'm just gonna need to find whatever, yeah. So it's just standard now, man. Q equals MC delta theta, yeah, delta T, which is basically gonna be M, which is 50, I'm pretty sure. If 50 plus 50 of the solution, yeah, that's what we're heating up. 4.18, because it tells us the heat capacity of the solution, yeah. And then the temperature change is 37.3, yeah, which you can find from just doing that minus that, yeah. Alright, calm. So that's temperature change, and that gives you Q, yeah. Q is gonna be equal to 7795.7 joules, yeah. And then from that, yeah, you can now find delta H, yeah, by basically making this into kilojoules, yeah. So delta H is gonna be that's 7, yeah. So delta H is basically gonna be equal to that, yeah, divided that in kilojoules, yeah, which is 7.796. So I rounded it to 96, yeah. And then divide that by the moles, yeah. It's going to be moles of not the excess, yeah, because that's not what reacted, yeah. You need to look at what actually reacted, yeah. So if I've got 0.05 of one thing and 0.08 of the other thing, then only 0.05 would have actually reacted of the other thing, right? Because if it's an excess, there's too much for it to react, you know what I'm saying? There will come a point where there's too much magnesium, there's not enough other thing to react, you know what I'm saying? Zinc sulfate to react, yeah. So the reaction would just stop in it, yeah. So therefore, yeah, 7796 here divided by the moles of the one in limiting factor, yeah, so 0.05 here, and that's gonna give me minus 156, yeah, minus because this is exothermic, yeah. And we know that as well because temperature increased, yeah. So it went from 23.9 to 61.2, yeah. Alright, calm. So minus 156, yeah. B. So this is most likely difference with a large difference between the student's experimental value and data book value, yeah. So for this one, yeah, you can't talk about it being different because of the data book is average mass because it says there's a large difference, yeah. So a large difference is probably caused because of heat loss, yeah. Because the average should be similar to what you get, you know what I'm saying, if you did it if it's done correctly, right? It shouldn't be that big, yeah. The reason it's that big is because of heat loss, yeah. Alright, calm. Another mad 6 marker, yeah. So let's get this one patterned, man. Calm. Again, they think they can throw you off with this, yeah, but they can't, bro. They just can't. You know what I'm saying? So, you know what I'm saying? They don't know about life hacks and that, bro, innit? They're gonna have to upgrade the testing system soon, innit? So using a polystyrene cup, yeah, or a lid effectively reduces, yeah, heat loss from the system, yeah. And by the way, yeah, you'll realize, it when you do bear of these questions, you'll realize they're all the same, man. So you might think, oh, how the hell did you know to mention that one, yeah? Well, obviously, because I have mark scheme in it, but on top of that, yeah, I could do without in it, but yeah, obviously because you practice in it, you see bare of them, and it's all the same shit in it. So just how the student's method and analysis of biology, you know what I'm saying? And biology is the same thing, yeah. In biology, there's also questions about no statistical test has been done and no whatever, you know what I'm saying? Not enough these larger sample sizes, it's just the same like bullshit points in it. Alright, calm, you just waffle, man. Additionally, so then also before adding the metal, yeah, record the temperature for a suitable duration, yeah. Which basically establishes an accurate initial temperature, yeah, because an initial temperature wouldn't be changing that much, yeah, because you did it for bare time, yeah. And then record the temperature values at regular intervals, yeah, to ensure comprehensive data collection, yeah. The white man will like this, you know what I'm saying? They'll like it when you mention, you know what I'm saying, yeah. They'll get hard to this, fam, yeah. So when you say comprehensive data collection, yeah, you know what I'm saying, yeah. At regular intervals, because obviously you take it at regular intervals, small intervals and whatnot, it makes it more accurate, yeah, compared to if you took it out like, what I'm saying, randomly, bruv, yeah. Makes it more comprehensive, yeah. Alright, calm. Plot the recorded temperatures, yeah, against time on a graph, yeah. And then we extrapolate the curve back, back to point. Compliment. And then obviously plot the recorded temperatures, yeah, against time on a graph and then extrapolate, yeah. Extrapolate the curve back to the point of addition, yeah, to estimate the maximum temperature which compensates for any heat loss, yeah. Alright, cool. Next one, yeah, state the name given to the enthalpy change, yeah. So this is basically what this is formation, bro, yeah. Easy, yeah. So yeah, we've got standard states here and we're just producing something, yeah. Calm. Explanation, yeah. So explanation, yeah, bro. Man missed the whole thing up here, bro. Alright, cool. Yeah, 15, yeah. Um, this question is about enthalpy change. Write a question including state how enthalpy of combustion. Yeah, so ethanol, bro, just write ethanol, which is this. Yeah, and that's gonna be liquid, and then just combust that. Yeah, so like I know when I combust it, yeah, I'm gonna need to mix it with oxygen. Yeah, and then always combustion creates carbon dioxide. Yeah, and H2O. And this is standard enthalpy of combustion, so it has to be complete combustion, yeah? And then you just balance it, yeah? So this will be 3, and then that'll be 2, and that'll be 3. Yeah? Calm. This one I already did, and then explanation, yeah? Well, why it's enthalpy formation, bro. What's the explanation? Explain why enthalpy change will be difficult to determine directly, yeah? Well, obviously it is different. It is. So they want to measure this enthalpy change of C with O to create CO, yeah? But it would be very difficult, yeah, to stop it from instead of creating it could easily just create CO2 instead of CO, which would mess up the whole experiment, yeah, and it's kind of difficult to prevent that, yeah. So that's why they can't just measure this enthalpy change directly, yeah. Calm. Next one. Standard enthalpy of combustion, yeah, for carbon and carbon monoxide, yeah, is that respectively. Use these data values to calculate the enthalpy change for reaction in part B, yeah. So fam. Or H here is going to be what? So that's easy. So combustion of carbon and carbon monoxide. So rather I'm combusting carbon here and I'm making carbon monoxide. So I just need to take the combustion value and then just flip the combustion value for CO because I'm forming it. So literally what I gotta do here is just literally write here minus 9 393, yeah. Come on, load. Alright, cool. Yeah, stop. I said stop acting up sometimes, you know what I'm saying? And then just flip this value. So instead of positive, it becomes negative. Positive. Negative becomes positive. Yeah. So 283. Yeah. That's gonna produce minus 110. Yeah. Calm. Because obviously I'm forming it. Yeah. I'm forming carbon monoxide. Yeah. So obviously I need to flip the value of combustion to formation. Yeah. Calm. Yeah. Next one. Use the following data to calculate the value for XE. F. Yeah. Calm. Mine. I've got you covered. Yeah. So again, this is a situation where you need to use like a Hess law, Hess diagram, yeah? Reason being is because, yeah, that's just how it works. You can't do this without Hess law, but I feel like Hess law is just a little bit easier, yeah, once you get the hang of it, yeah? People, they find it hard to get the hang of, yeah? But once you get the hang of it, it's an important tool. So basically, yeah, let's just write this equation out fully. So xe plus 2f2 would produce xef4, yeah? And I want to find how much in this xef, yeah? So you can already see which one I'm trying to find, yeah? And then, what I can do, yeah, is I can say, how much to make F4? I need 4F, so I need XE, yeah, plus 4F. So this would be the formation, yeah? Calm. Yeah, and you can go either way. You can make this arrow go down or up, it doesn't matter, yeah? I can do that, it doesn't matter. Calm. And then this goes there to there, yeah? Because actually it'll be that way because enthalpy, bond enthalpy, yeah, is how much energy is needed to break the bond. So I need to break this bond back into its constituent, yeah? So it would actually be the combustion, yeah? And then this way, it's plus 148, so I'm going from F2 to 2F. So from F2 to 2F here, I'm going down. Yeah. So again, and there's down here is 158. But because I'm going from 2F2 to 4F instead of F2 to 2F, it would have to be 2 times 158, yeah? Calm. Yeah? And then also on top of that, yeah, this one is minus 252, as it says. So therefore, if I'm modifying XE F4 to there, yeah, it's easy, yeah? All I need to do therefore, yeah, is just I can go either route, yeah. It will be essentially 2 times 158. So it'll be so I can flip this, so it'll be 252. And then plus 2 times 158. So if I want to go from XEF to this one, yeah, to break the bonds here, I can just flip this, so it'll be plus 252 plus 2 times 158. then and it's gonna give me 5, 6, 8, yeah? And then deep it. That's that to there. So then that's equal to that. So going from xe of f4 to that is the same as going from xe f4 to xe plus 2 f2 and then downwards, yeah? And then deep it as well. How many am I creating? How many bonds are there? There's 4 xfe bonds, yeah? So therefore I need to divide this 5, 6, 8 by 4 because there's 4 xef bonds, yes? Then it'll be 142. So that's the final answer. Calm. So just the reason why the calculated and the different from the bro. Yeah, it's getting a bit repetitive, man. Easy, but when it's repetitive, it's easy, you know what I'm saying? It's meant to be repetitive. So again, yeah, so mean bond enthalpy would be made from like taking the XEF bond, yeah, how much to break that in a range of different compounds, yeah, then taking the average, yeah, whereas we're just taking one compound, yeah, so it's gonna be different. 16. So for this one, yeah, read the question. It's pretty long, yeah. I'm not gonna lie, but essentially what you need to do, yeah, is you need to basically just find the change in temperature, yeah, and then basically use that to find the enthalpy change. To calculate enthalpy change, yeah. So what I can do here, yeah, is I need to extrapolate this correctly, yeah. So the way that I think I did it here, yeah, is I did this. So I did it around here, and then here, this question I actually want a straight line because it's curved so much, yeah. They want it to basically just be straight up to the fourth minute, yeah. This goes to the fourth minute, yeah. So we'll go all the way out here. So extrapolate that forward a bit, and then this one you need to just take it like this. It's a bit techie. It's a bit techie still, yeah. And that would have been basically 20, yeah. Wait, 5 in it. 20. So basically, if you take each individual point here, if I zoom in a bit here, that'll be 20.5. So that's that's 21. That's 22. And this one will be 23. Yeah. And this one up here, so 20.5, 21. Yeah, around that value, innit? And then this one, they want it to be like around this value. So you see how it's slowly kind of increasing in a way, yeah? So it needs to be like you need to make this straight as possible, yeah? And then just keep going until it reaches around 40 basically. It should be a straight line, yeah? It needs to basically reach around 40 when it gets to 4. So something like that, similar to that, yeah? Then you just take the difference here. So it's actually going to be like around 23 or whatever, yeah? And this is going to be around 40. Why is it not? Yeah, it's crashing it big time. It's minor. Yeah, and if you take the temperature change, it should be 17. So that's ideally what you need to take here. It would be 17, yeah? That's the temperature change the mark scheme wants, yeah? But this one's a bit techie still. But like it doesn't matter if it's a little bit off here, they won't like look at it too much and it's minor. Yeah? But essentially it should be 17, yeah? And so yeah, so take that, it should be a straight line, kind of going with the general trend all the way to a 40. You need to extrapolate all the way to the fourth minute here. Extrapolate this course all the way to the fourth minute. And then yeah, calm. Because the reaction happens around the fourth minute, yeah? Pretty sure. 3 minutes after adding, yeah, at the fourth minute, yeah. Alright, calm. So now that I've got that, yeah, delta t from the graph here, you just find q equals mc delta theta, yeah? Which is gonna be m is 10, because look, 10 for AQ is here. And then C is 4.18. And then delta theta would be 17. Or delta t would be 17, yeah? Then in total that gives you 710.6. Yeah? Calm. And then if you want to take the enthalpy change here, you need to do delta H here. It's going to be equal to Q over moles. Yeah, and to do Q over moles here, it's basically going to be 7. I need to find the moles here, so moles of magnesium is equal to the mass here over the MR. The mass is 0.24 from the question. The MR is 24.3, which is from periodic table. So wait a second to load in. And then, yeah, and that would basically give you 0.00988 mole. Yeah. So then here you just need to do basically 710.6 over that, yeah. That's gonna give you some mad number like basically 72,000, yeah. So then that's basically gonna be the same as 72, yeah, kilojoule per mole, yeah, because that's gonna be in joule per mole, so you exchange it to kilojoule per mole, and then it's gonna be that, yeah, and it's gonna be negative as well, yeah, because the temperature is increasing or whatever, yeah. So it's negative, yeah, exothermic, yeah, because the temperature increased from down there where the initial was, yeah, all the way to the top as you saw, yeah. So that's exothermic. All right, cool. Next one, nearly done, yeah. Question 17. Again, I need to do some Hess cycle situation here, yeah? So let's do that Hess cycle, yeah? So um what we need to write here yeah, is again, so I've got the that to that, yeah? So let's just write that down. C2H6 here plus 6F2 produces here C2F6 plus 6HF here. Calm. Then I need to go with their constituent elements here, so CF and H. Yeah, so to go from CF to H to this, I'm essentially only making, because remember, elements don't have a formation, yeah? Enthalpy, yeah? Because you can't form an element, yeah? From a constituent element, that doesn't make sense, yeah? So your CFH here goes to this. I'm going to be producing C2H6 here, which is basically minus 84, yeah? To produce that as the formation value. And this formation is minus 2898, okay? And then deep it from here to here, yeah? To form C2F6 is minus 1344, yeah? But I'm also forming 6HF. So the HF bond is what I'm trying to find here, yeah? How many HS bonds I have? I've got 6, so I can say plus 6Y, yeah? And now again, what I can say here is that going from CFH here to C to this, so from there to there, yeah? Same as going from there up here where my mouse is, yeah? So here to here, and then from here to here. Does that make sense? So what I can just say is just equate it basically, yeah? Just say minus 84 minus 2898 is equal to minus 1344 plus 6y, yeah, and then just find y. It's loading, don't worry. Like, it's taking some time still, it's taking some time, and it's breathing, it's breathing, it's breathing. Now, yeah, now it. I think you should take this time to basically just breathe a little bit, yeah. Alright, calm. Alright, so now it's here again, yeah. So now you just need to basically rearrange this here. So find 6y, and then basically what you'll find here is that y is equal to minus 273, yeah? Minus 273, so it'll be B. Just taking some time to reload. Yeah, so minus 273, yeah. Alright, calm. So that's essentially what that's how you do it, yeah. So just from CF to there and then there to there, combine that, so minus 84 minus 2898 is equal to the same thing as this. Because this root to that root is the same as that root to that root, yeah. And then after that, yeah, you just bring this 1344 to the other side, divide by 6, you get y equals minus 273, yeah. Calm. Final, nah, fuck, man, it's still bare. Alright, cool. It's minor, yeah. What is the temperature rise in K when 504 joules of heat energy is absorbed by that, yeah? Let's see, mate. It's calm, yeah, it's calm. Keep the morale up, yeah. Calm and firm, yeah. So let's do this, yeah. So basically, yeah, Q equals MC delta T, yeah. Bun the whiteboard for not allowing me to, you know what I'm saying? Making it laggy, yeah. Q over MC, and then Q is just 504, yeah. And you want to divide that 504 by M times C. M, yeah, is basically just 110 because it's 0.110 kilograms here, which is the same as 110 grams here. You get that? So if it's 110 grams here, then you can times it by C, which is 0.488, 448. Easy. Yeah. So 110 grams times. By the way, this is because it's an iron, yeah. You know how I normally talk about the water, yeah? There's no water here, it's just heating up some iron, bro, yeah? That's why. That's why I'm taking the measurement of the iron. It's not a calorimetry kind of thing, yeah? That's going to produce here 10.23K. So 10.23K is basically B, yeah? I can't let that load. Calm, yeah? So that's going to produce 10.23K, and that's going to be B, yeah? Minor. Alright, calm. 19. 19 is easy, yeah? It's just basically bonds made minus bonds broken, but essentially, yeah, there's no need for this because it's just combusting this, yeah? So it's just breaking this. So actually all you need to do here is just find how many moles here of each bond. So it's just gonna be, it's easy, man, yeah? There's gonna be three, not three, there's two CC bonds here. So two CC, CC is 348 plus seven CH bonds here, just 412, and then plus one CO bond here, which is 360. And then plus one OH bond, which is 463, yeah? And that's it. If you add that in total, that will give you the... If you add that in total, yeah, that would actually give you the enthalpy, yeah? Which is 4403, so C, yeah? Column. Reason being is because you're just breaking one of them, yeah? So you're just breaking all the bonds to produce the standard bonds. You see what I'm saying? That's why I don't need to do the like left minus right hand side. Doesn't make sense because you're not making any compound here. You're not making any bonds on the right hand side. Yeah? Alright, calm. So you're just breaking them. So that's all you need to do, yeah? So just draw the structure of that if you don't understand this, yeah? But essentially, it's just two CC bonds, because deep hit two CC bonds, yeah? And O and then H here. So there's going to be one CO bond, one OH bond, yeah? And the rest are just hydrogen bonds, yeah? So 7H bonds, yeah? Or CH bonds, yeah? Alright, calm. Last question, question 20, yeah? Well, it's bare, but it's technically last question, yeah? So easy. Write an equation for the complete combustion of leaf alcohol, yeah? So leaf alcohol, if you look at this equation, is basically just C6H11OH. Come on, calm. Yes, on life support, fam. Then you're gonna add oxygen here, and that's gonna produce CO2 as it always does, plus water, yeah? And then you just balance it. So yeah, come on, come on. My brother, yeah. Come on, fam. power through this. Alright, calm, yeah? Loaded, yeah? So therefore, yeah, then just balance it. So it's gonna be 8.5 here. It's gonna be 6 here. It's gonna be 6 there, yeah? Easy. Easy. So find the enthalpy here. Combustion, yeah. So I need to find Q and then divide Q by the moles of alcohol and then easy, man, yeah? Easy, 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 yeah? Home run, fam, you know what I'm trying to say? Q is equal to MC delta T, fam, yeah? MC delta T, yeah? How many M do I have? I've got 50, yeah? How many C's do I have? I've got 4.18, yeah? How many delta T do I have? I've got 20.1 allegedly, yeah? But let me just show you in a minute, yeah? My what's even mad, not gonna lie. Alright, cool. Nice, yeah. So and then the initial temperature, mass final temperature, so that's where I got all this from, by the way, yeah. The mass was 50 because that's the 50 grams of water. And then this is the actual mass I'm gonna use to find the moles, and then I'm just gonna do final temperature minus initial temperature to find the temperature change, yeah, which is 20.1. Yeah. Alright, calm. That's gonna give me Q, yeah, of 42.01 joules. Calm. Yeah, just bear with it. Calm. Yeah, and then I just need to find moles, yeah. So moles of alcohol, yeah. I'm just gonna call it OH, yeah, but to save time, yeah. So moles of alcohol is gonna be the actual mass of alcohol, which was 0.54. If you took the final mass minus the initial mass, yeah, and then divide that by the MR of the alcohol, yeah, which is 100. I'm pretty sure. So wait. Take this time while you wait, you know. Just appreciate the surroundings, yeah. Appreciate life in general. You know what I'm saying? A levels and shit. Again, so that's taken from there, yeah. But that minus that, yeah. You get 0.0. You get 0.54, yeah. If you take the top thing from the bottom thing, yeah. And then I mean final from initial, yeah. Yeah, calm. Because some mass was used, that's the mass used, yeah. So you need to do the initial minus the final, yeah. And then yeah. And the moles is 100, I'm pretty sure of this shit, yeah. The MR. Doesn't even tell you the MR, yeah? You just actually find that. So find the MR using this. So it's 12 times 6 plus 11 times 1 times 16 plus 16 plus 1, yeah? Don't know why they're being dickheads about this. But yeah. Just find that and you'll have an MR of 100 anyway, yeah? Alright, calm. And then basically, yeah, that's just going to be 0.0054 mole, yeah? Calm. And then, yeah, take that value you found earlier. So to find delta H here, you need to find Q over that. So do 4201, yeah, divided by 0.0054, yeah? And that's going to give you the joules per mole, yeah, which is 778,000. Again, while it loads, just, you know, write it down, appreciate situations, man. Drink some water, drink something, you know what I'm saying? It's times like these, you know what I'm saying? You need tranquility in that, you know what I'm saying? For the A levels, you know what I'm trying to say? Yeah. This channel is just about patterning everyone, you know what I'm saying? Don't need to, you know what I'm saying? Don't need to listen to teacher, anyone from whatever situation, whatever background, whatever, you know what I'm saying? Environment, yeah. Can easily just look at this video, learn, see how to do the questions, everything. And yeah, they're basically patterned, man. I don't know why it's taking so long to load, man. It's minor. I'll keep this in too. You know what I'm saying? Yeah, we've got to struggle together, same way how we win together, yeah? So every single part of this here that lags here, you need to see it together, you know what I'm saying? Yeah? So all of you man are, you know what I'm saying, in the same boat, yeah? We're all in the same boat. Alright, calm. So that's what it gives us here, and then Drupal more, yeah. I don't need to convert it to kill Drupal more because it says just give me it says just state the units here, yeah. So I can just state the units. Alright, calm. State why B is likely to differ from the value quoted. Bro. It says state how, so the reason why is like how different would it be, yeah? It'll be less negative. Due to some heat loss here, it'll be less negative, whereas the data value will be accurate, yeah. So it wouldn't be it'll be more negative, yeah, because more heat. And you measure how much mass of that, yeah, basically, bro, just measure 50 centimeter cubed, yeah, of volume, and then water has a known density, yeah. So grams can be calculated from that. So to find water, obviously water has a known density of 1, yeah. So because it has that density of 1, therefore 50 centimeter cube of water, yeah, would just be 50 grams, yeah. So that's how you'd find 50 grams, yeah, without using a balance, yeah, because you can't measure 50 grams of water, yeah. So you just find the volume and then change it into grams, yeah. Calm, that's it, yeah. Easy, man, yeah. Whole thing completely done, yeah. Completely patterned, yeah. Let's do a look at zoom out thing, yeah, just so you can appreciate the scale, you know what I'm saying? Yeah. Trust me. Yeah, come on, I feel like you know what I'm saying, completed something, yeah. Calm, saying that, see you, man, yeah.